So to start, are there questions on stuff that we've been doing so far? Yeah?
Well, is there a clever way, I guess, to do the problem on the assignment where you kind of find the logical polys? Given that
Sorry, let me look at the problem. Clever way.
Would it be helpful if we said what the non-clever way is that we have? What we think is non-clever is just like use the stabilizers to project to find the code words and then list out all your code words and be like, okay, what maps these to each other in a way that looks like polys?
Yeah, okay, so that's probably not the most clever way.
Yeah.
So a better approach, I mean, so the logical polys, remember, are elements of N of S. So what you have to do is you have to write down things that commute with the stabilizer but aren't in it. And then you can just kind of start assigning them the logical polys. It gets a little bit tricky because you have to make sure they commute and anti-commute with each other in the right way. But for this size code, it's kind of not too hard to do it by hand.
That's much easier.
Yeah, I mean, so and if you want to do even easier, remember that if you look at the binary symplectic representation, that that this is, the stabilizer is a matrix, basically, and that commutation boils down to a linear relationship, right? This symplectic inner product is 0, and so then it's basically just a linear algebra problem to find things that commute. Now, I mean, in the previous problem set, I gave you questions like, what's the distance of this code? And that's something that doesn't have a good solution in general. And it's just relying on the fact that these are small codes that you can kind of work this out. But but finding the normalizer, that's something, because it's basically linear algebra, is something that's fundamentally not a difficult problem, that it scales easily with the system size.
I must have this wrong. I thought the size of the normalizer was d to the n plus r.
No, it's 2n. Well, if r is the number of generators, it's 2n minus r. It's n plus d to the n plus k, where k is the number of logical qubits.
So it would have been for this one 3 to the 4 plus 2, so 3 to the 6 elements of the normalizer.
Right, but you don't have to write them all down.
Right.
You just have to write a generating set, and there's 2 logical qubits here. So that's 4. This is a logical x1, a logical x2, a logical z1, a logical z2. Yeah, specifically, that's what I asked for, right? Coset representatives for xi and zi. Any other questions? Okay. So what I wanted to do today was to continue to talk about the Clifford group. So last time I showed you the definition and kind of standard elements inside it, and explained that it was sufficient to kind of keep track of what happened to polys, right? That if you knew the conjugation action on the polys, then that completely specified the unitary up to some global phase. So the first thing I want to do today is kind of take advantage of that observation. And I guess I mentioned this last time. So if you write down a unitary, it's a 2 to the n by 2 to the n dimensional matrix, 2 to the n by 2 to the n matrix, right, on n qubits. So that's a very big matrix. It has exponentially many entries. But keeping track of the polys, remember, you only need to keep track of the generating set, right? You need to keep track track of the x's and z's and how they conjugate. And everything else can come out. And that's just 2n elements. So, so what you can do is you can take advantage of that to say, well, suppose I have a circuit that's made up of Clifford group gates, only Clifford group gates. Then I can figure out what's happening to it. I can figure out what the circuit does just by tracking its conjugation action on polys. So here's an example. To show you how it works. So this is just 2 qubits. So obviously, you're not really gaining a huge advantage, maybe no advantage at all by looking at the polys, because it's a 4x4 matrix versus keeping track of 4 things. But it'll show you how this idea works. And if you scale it up, then you do start to get a big advantage. So this circuit of 3 C0s, maybe some of you have seen it before, maybe not. But we're going to figure out what it does by keeping track of what happens to polys. So let's write down the x's and z's. And remember, anything else is going to be a product of these 4 things. Okay? And see what happens to them as we do each of these C0s. Right, so the first C0, remember, what does the C0 do to polys? It takes xi to xx. Ix goes to ix. Zi goes to zi. And iz goes to zz. OK? So that's just from last week. Now, the second C0, well, it does the same thing, but it's going in the opposite direction. So we have to think about doing it the other way. So for instance, this one, now the x is in the control. So that's going to go to xx. And this one, the z is in the target. So that's going to go to zz. If you take a normal rule and flip the 2 qubit. OK, this one and this one are a little more complicated, right? Because they're not already written here. So xx, that's the product of xi and ix, right? So xi would go to xi. Again, remember, we're flipping the control and target. And ix would go to xx. So what we want is the product of xi and xx, which is ix. OK? And then the last one, similarly, zz is the product of zi and iz. Zi would go to zz, and iz would go to iz. And the product of those is then zi. And maybe it's worth pointing out that if you compare the commutation relations of these things with the ones at the beginning, they're going to be the same, right? So for instance, xi and zi started out anti-commuting, and here we have that corresponding to ix and zz, which anti-commute. Whereas xi and iz, they commuted, and ix and zi commute. OK, so it all works out right. OK, and then one more C0. We're doing the same sort of thing. But now the control is the first qubit again. So ix will go to ix. And this will go to the product of xx and ix, what you get from xi and ix. And so xx times ix is xi. And this goes to the product of zi and zz. So you get iz. And this just goes to zi. OK? So this tells us what the overall effect of the circuit is. It takes xi to ix, ix to xi, zi to iz, iz to zi. OK? And if you look at this, you see that what's happened is the first and second qubits have switched places, right? In every case, the xi, zi, the first qubit have gone to the second qubit, and the ones on the second qubit have gone to the first qubit. And so what's another gate that does that? Well, the swap gate, the gate that swaps those two qubits, right? That will definitely have the same effect. And so we can immediately identify this circuit as the swap gate. Okay? Did everyone follow that? And you see how he's getting this logic not from writing down the matrices, but by just cracking the polys. And so if you had an n qubit system, well then you know, at any time, keeping track of the state here requires you to keep track of 2n polys, so O of n squared bits of memory, compared to the 2 to the n by 2 to the n matrix that you'd need. And to do an update is actually even faster, because if you have n qubits, but you're only doing one gate, it can only affect up to 2 qubits, right? If it's a 2-qubit gate. If it's a 3-qubit, well, yeah. Let's assume that we just have the kind of the basic Clifford group elements that I talked about last week. So a 2-qubit gate is the most you can have. And so if you had, you know, tensor other things, those wouldn't get changed by this 2-qubit gate. So you only have to update your record of the transformation for the qubits that the gate is affecting. And so that only requires O of n steps update. Whereas, you know, again, if you're writing them down as big matrices, you're not getting any obvious savings. You still have to potentially update, you know, 2 to the n by 2 to the n, 4 to the n different matrix elements. Okay. So hopefully you can see now, if you have any circuit of unitary Clifford group operations, how you can follow its evolution. And you're going to have on the problem set, I've asked you to do that. Okay, so then the next thing to ask is, what about measurements? So suppose you have something like this and you want to do a measurement. Can you figure out what the result is? And if it's just a partial measurement, if you're only measuring 1 qubit, can you update it? And it turns out that yes, you can. Write it here. So suppose we start with initial stabilizer state. And we want to do a circuit which is made up of Clifford group gates, Pauli basis measurements, and even Clifford group gates which are conditioned on classical information. So in particular, we make some measurements, we get some classical bits output, and then based on those classical bits, we might want to do one or the other Clifford group gate. So then this whole thing can be simulated on a classical computer. And it takes O of n squared gates per quantum gate. So what I'm going to show you is actually going to use O of n cubed, but it can be improved by using a slightly more efficient approach. Okay, so the upshot is that any circuits you make like this, which includes all the circuits you need to encode a quantum error correcting code and to do error correction, can all be simulated efficiently on a classical computer. Okay, so if it just contains Clifford group gates, then definitely you're okay, right? Because that's what we did already. So we're starting with an initial stabilizer state. So we start out with some stabilizer, and well, the Clifford group circuit, we can figure out what happens to every Pauli this way, and so we know the final stabilizer. So the thing that's going to be tricky is going to be simulating the measurements. So how do we do that? I guess I should say that this is usually called the Gottesman-PI theorem. Okay, so how do we simulate the measurements? So basically there's going to be two cases. Well, kind of three cases. Let's break it into two cases. So case one. So suppose we want to measure the eigenvalue of some Pauli P. Okay, so you can just think of, if we want to measure a single qubit in the standard basis, then we'd be measuring the eigenvalue of z on that qubit, right? So that can be your example if you want to think of a concrete case. So case one is if plus or minus p is in the stabilizer. So yeah, so the situation we're in, remember, at any given time, we have a stabilizer to describe the state. And I want to first figure out what the outcome of the measurement is going to be. And second, update the stabilizer, conditioned on the measurement outcome. And then case two is going to be if neither of those is true. So neither p nor minus p is in the stabilizer. So first of all, we have to know how we can tell. Is p in the stabilizer or minus p in the stabilizer or not? So the way to determine this is actually closely related to what I just told you in response to the question. So figuring out things that commute or anti-commute is basically a linear algebra problem when you go to this binary symplectic representation. Yeah, maybe I can call it X. Okay, so stabilizer S, which will be generated by Wi in symplectic representation, okay? So Wi are generators of the stabilizer. Vectors representing generators of the stabilizer. And V sub p is going to be the binary vector representing p. And so we have this set of equations. And if this is true for all I, then that means that VP, which is kind of P script of the phase, well, it means that P commutes with everything in the stabilizer. And since this is a stabilizer state that we're dealing with, there's it's like, you know, a code with k equals 0. So there's n generators and n qubits, and actually n of s is equal to s. Well, it's not exactly equal to s. N of s mod phases is equal to s. Because n of s includes everything that commutes with s. S can't include -1, right? It's just the abelian. I mean, it's just the kind of the straight things that you get from the generator. And so plus or minus I is actually not really going to be an issue, but it could be that P or minus P is in S, but they can't both be. So anyway, so the upshot is you can tell whether you're in case 1 or case 2 by calculating these things. Okay? That's just totally straightforward calculation that you do, right? It's not, you're not even, you know, inverting a matrix or anything like that yet. We will do that in a minute. But so this is a very easy thing to check. And if it is the case that this is true, then plus or minus P is in the stabilizer, and you're in case 1. And then you need to figure out whether it's plus P or minus P. Why do you need to do that? Well, if plus P is in the stabilizer, then when you measure the eigenvalue of P, it's going to be +1, right? Because that's the definition of being in the stabilizer. Whereas if minus P is in the stabilizer, then when you measure the eigenvalue of P, it's going to be -1. Okay, so we need to find out plus or minus P. And to do that, you need to write this vector VP as some sum of the vectors Wi. So again, we're going to the binary symplectic representation. And this, again, is a linear algebra problem, right? And if all you have around is the things Wi, then you have to do this kind of matrix inversion to do it. And this is the main place, I think, where you can go from order n cubed to order n squared by doing something more efficient, by keeping track of kind of more information. But again, this is a linear algebra problem. And then you determine the CIs. And that tells you that plus or minus P is so suppose Wi corresponds to Mi. And plus or minus P is then going to be the product of Mi to the Ci. Okay? And so you can just multiply this out and determine whether it's plus or minus that way. Okay? You see, this is something that you cannot figure out just in symplectic representation. Well, you can, but you have to absorb in all the information that's in the polygroup anyway. Right? Because the symplectic representation is losing exactly this information about phases. Right? I mean, so for instance, so multiplication in the polygroup corresponds to addition in the symplectic representation. And addition is commutative, right? So if you take, you know, the x vector and the z vector, 1, 0, and 0, 1, and you add them together, you get 1, 1. And it's true whichever order you do it in. Whereas if you do it in the polygroup, in one case you get IY, and in one case you get minus IY. Okay, and that sign now matters. So this is something you must do in the polygroup, effectively. And then you get this result. If plus, then the output is 1 plus 1. And if it's minus, then the output is minus 1. Okay, which you might represent as bits, 0 and 1. Okay? Does everyone understand case 1 here? Okay, so case 2 is actually the more interesting case. So in case 2, this is not true. We've determined that P is not in the stabilizer, and that minus P is not in the stabilizer. And that means it's not even in n of s, in fact. And along the way, we calculated these symplectic inner products. And we discovered that it was not in n of s by discovering that one of these symplectic inner products gave us 1 instead of 0. And so in particular, there exists some I such that Mi and P anti-commute. Okay? So the first question is what's the outcome of the measurement that we make? And I claim that the outcome is just a random bit. It's equally likely to be plus 1 or minus 1, or 0 and 1. So how do I know that? Well, so if we look at this expectation value, so P is a Pauli, right? It has a plus 1 eigenspace and a minus 1 eigenspace. And so the probability of getting the plus 1 eigenspace is the projector is psi pi plus psi, where pi plus is projector on the plus 1 eigenspace. And the probability of getting the minus 1 eigenspace is psi pi minus psi. But P is pi plus minus pi minus, right? If you look at it in its eigenbasis, it's plus 1s for one subspace and minus 1s for the other subspace. So this is the probability of plus minus the probability of minus. Okay? And so remember, psi is in the stabilizer, so we can insert m in here. Sorry. So this is true. And P and M, Mi anti-commute. And then we can absorb the Mi back into psi here, and we get minus psi p psi. So psi p psi is equal to minus psi p psi, and therefore it's 0. Okay, which says that the probability of plus and the probability of minus are equal. Okay, so to determine the outcome, if in our classical simulation, to determine the outcome, this measurement, we flip a bit, and that's the output of the measurement. Okay, so then the last question to ask is, what state do we have left over, right? If we have n qubits and we've just measured one Pauli, there's still at least, I mean, say you measure one qubit, you know the output on that qubit, but there's still n minus 1 other qubits left over. And you want to know what their state is conditioned on your measurement outcome. So, so my claim is going to be that the state is still a stabilizer state. And so we want to update the stabilizer to take that into account. Okay? So what is in the new stabilizer? Well, one thing that we know is in the stabilizer is the thing we just measured, right? We just measured, say, the plus 1 eigenstate of P. So that means that p psi is equal to psi. Right? So p is in the stabilizer. If we got the output minus, then it's minus p that's in the stabilizer. So we definitely need to put plus or minus p in S prime. Well, okay. Okay. So now let's look at the things that were already in the stabilizer. So are they still in the stabilizer or not? So suppose we have some generator mj where mj and p commute. Right? We know that p anti-commutes with mi, but it could certainly commute with some other stabilizer element. Well, in that case, so the new state is going to be the projector, depending which sign we got, 1/2 I plus or minus p applied to psi. Okay, so let's apply mj to this and see what happens. So mj psi prime is equal to 1/2 mj plus or minus mjp psi, which is, well, mj and p commute, so we can move this past. And so this is 1/2 I plus or minus p mj psi. Which is the mj gets absorbed into the psi because psi mj is in the stabilizer of psi, and so this is just psi prime again. Okay, and so that means that mj, when mj commutes with psi, is still in the stabilizer. So that gives us a bunch more elements of the stabilizer. Okay, so the problem is we don't know how many of the original generators commuted with p and how many anti-commuted. It could be any number. I mean, it has to be at least one that anti-commuted. But other than that, we don't know anything. So let's look at the case when mj and p anti-commute. Well, in that case, it's hard to know, right? Because in fact, you can well, okay. Suppose you do this same argument. Okay, what you'll find is that when you move this mj past the p, you get, instead of I, if you started with I plus or minus p, you ended up with I minus or plus p, right? And so now, instead of a projector on the +1 eigenspace, you have a projector on the -1 eigenspace. Okay, and those are orthogonal. So actually, it's definitely not an eigenvector of mj when mj anti-commutes with p. So that's not going to work. And if we had many such things that anti-commute, then clearly this is not the whole stabilizer. But when mj and p anti-commute, the thing is we know that there's one generator that definitely anti-commutes. And then mi mj will commute with p. Why? Well, if you move mj past p, that gives you a -1. And when you move mi past, you also get a -1. So the product gives you +1. Okay? And we know that if mi mj commutes with p, and mi mj is in the initial stabilizer, right, because both of these things were. So by this argument up here, that implies that mi mj is in the revised stabilizer. Okay? So how are we doing? Well, how many generators do we have now for S prime? Well, this is one generator. This is some number of generators. We don't know how many. This also by itself, we don't know how many. But taking these together, for every j that's not equal to I, one of these two things has to be true. Okay? And there were n generators to start with, n minus 1 plus I, the special one that we've picked out here. And therefore, together, this gives us n minus 1 generators of S prime. Okay? So altogether, we have n generators, which is great. That means that we've completely specified the stabilizer. I guess you might ask, well, how do we know that these are independent, right? Maybe some of them are products of the others. Well, we know that P cannot be a product of anything, any number of mi's and mj's, because it's not in the stabilizer. Okay, nor is minus it in the stabilizer. So this is definitely different. And if you look at these, well, there was a problem on an earlier problem set that showed this, but the most straightforward thing to notice is that if you had some product of these things that was non-trivial, each mj can only appear once. Right? It's either up here or up here. So if you have some non-trivial product of these things, then that means you have some non-trivial product of the mj's and maybe mi that's giving the identity. And we know that can't happen because the original thing, they were independent. Okay? So really, this is the new stabilizer. Okay, so how long does it take to do this? Well, so we've already determined whether this was true, and in the process, we figured out this value mi. And so all we need to do is go through each of the other generators and update it. We say, okay, we replace mi with p or minus p. So that's some order n thing. And then for each of these other generators, we say, does it commute with p or anti-commute? If it commutes, we leave it alone. If it anti-commutes, we multiply it by mi. And so for updating each generator, it takes at most O of n time. And so the whole thing, this whole step, takes O of n squared. Okay. So that shows how you can simulate the Pauli basis measurements. And then the last thing, Clifford group operations conditioned on classical measurement outcomes, well, that's actually just kind of trivial, right? Because everything that we've done is we're talking about a classical simulation, right? And so if we decide to do this step or not decide to do this step based on some classical thing, that just is still easily classically simulatable, right? And so that's the end of the theorem. Okay? Now, the reason, I mean, there's a couple of reasons why it's interesting to add this last thing about Clifford group operations conditioned on classical gate. One is because it actually shows up during fault-tolerant procedures that you want to do this sort of thing, although usually not with an initial stabilizer state. But it is the type of thing that can show up in circuits. And the other is the observation that Clifford gates, so if you kind of purified a Clifford gate conditioned on classical bits and had it Clifford gate conditioned on a quantum bit, then that would be something that's outside the Clifford group. Okay, so for instance, the controlled NOT gate. Or you say you do a controlled NOT gate depending on whether this bit is 0 or 1. That's the Toffoli gate. That's a 3-qubit gate. And if you work it out, that's not in the Clifford group. This is kind of getting you halfway to those other gates. It's only conditioned on classical information. But it's showing you that there's actually a little bit more power here than you might expect. Okay, So let's do an example of how this this measurement updating works, so that you can kind of get a better feel for it. So the example, hopefully this is a circuit that you do recognize. So I'm going to do an example where we actually don't have a stabilizer state, but some set of possibilities. So it's kind of a not completely specified stabilizer state. And so this state is going to be some psi, and this is an EPR pair. So this is 0, 0 plus 1, 1. And then we're going to do a Bell measurement here. And let's see, I have to get it right. Measuring because it's X basis and Z basis, I think. Yeah. And then conditioned on these measurement outcomes, we're going to do some poly here. Okay? This, of course, is the quantum teleportation circuit. And so, of course, you know, there's a lot. This was derived long before stabilizers and anything like that. So certainly you can do this in the standard basis representation. But it turns out to be exactly the sort of circuit that's covered by this theorem. Okay, it has Clifford group gates. It has stabilizer states. It has Pauli measurement. And it has even things conditioned on Pauli measurements, although admittedly they're Pauli conditioned. And so let's see how this plays out. So to describe this initial state, we're going to use kind of a mixture of just tracking the stabilizer and tracking all the Paulis. So this initial state, well, 0, 0 plus 1, 1 has stabilizer x, x, and z, z. Okay, so the first qubit, though, is not here. So this is just the second and third qubits. So we start out with this stabilizer. All the states, the input states, will be +1 eigenstates of these things. And then we have a logical x and a logical z. And those are x, I, and z, I. Okay? And so now we want to keep on updating these through the whole procedure. Okay, so the very first step then is this controlled NOT gate. So we have to update all of these things. So IX, remember, goes to IX. So this first generator goes to IXX. But IZ goes to ZZ. So this is the new stabilizer. And the new logical X, well, XI goes to XX. And ZI goes to ZI. Okay? Is everyone following so far? Okay, so that's the unitary gate. So now let's do a measurement. So let's measure the first qubit in the X basis. Okay, so let's say we get the output bit A, and here we're going to get B. So what are we doing? So X on the first qubit, first of all, we have to see if it's in the stabilizer or not, or minus X. Well, it commutes with this, but it doesn't commute with this. Okay, so it's not going to be in the stabilizer. We're in that case 2 down there. The output is going to be a random bit, so that's consistent with what we know about teleportation. The output should be, classical bits should be random. So A is a random bit, and then we replace this anti-commuting stabilizer generator with plus or minus X, right? So it's going to be -1 to the A, X, I. And this generator here just stays because it commutes. And now the logical Paulis, X bar and Z bar, they kind of work the same way. That if they commute, we leave them alone. If they anti-commute, we have to multiply by this thing that we're replacing. Okay, so this one here, XXI, that commutes with X. So that's going to stay. This one down here, that anti-commutes with X. So that can't stay. But you know, this is a coset, represents a coset of the stabilizer. And so if you multiply by this stabilizer element, you get a different representative of z bar, like IZZ. And IZZ does commute, right? And so basically, we're just implementing this C rule here. It's just for the logicals instead of the stabilizer elements. So this becomes IZZ. OK. So the next step, then, is to measure the eigenstate of Z on the second qubit. We get the output B. So again, let's see. This generator anti-commutes. This generator commutes. So this one's staying in. And this one gets replaced by -1 to the B IZI. OK? Now the logicals. So here's where things start to get a little bit tricky. So, with Z on the second qubit. So this one is staying in there. That's fine. So we have IZZ. This one has to go because it anti-commutes with Z on the second qubit. So what do we want to do? We want to multiply. OK, I guess it's not that tricky. We're multiplying by this thing that's coming out. It's the next step that's maybe a teeny little bit tricky. And so we're getting XIX. OK? And so this is our new state. We have this stabilizer, which is just saying that the first two qubits have the values A and B. And these are the logical things. Now, the thing is that at this point, we'd like to kind of throw away the first two qubits. But we can't do that in this representation because the logical qubits still involve these first two qubits. But luckily, we can still get rid of them because remember, these are just representatives of some coset. So if we multiply by an element of the stabilizer, we'll get a different representative of that coset. So this state here is really the same. Well, we're going to write the same stabilizer generators here as if we take this and multiply it by this, right? Because then we're going to get IIX. And the first two qubits are not relevant anymore. But we have to keep track of this phase. So what we're really getting here, is -1 to the A IIX. And similarly, we want to multiply this by this. So we get -1 to the B IIZ. OK? And so now our very last step is to do a Pauli that's conditioned on A and B. And what we want to do is we want the output to be psi again. Right? So what would it mean if the output is psi? Well, that would mean that the logical X should become X on the last qubit. We're almost there, but the phase might be wrong. The logical Z could become Z on the last qubit. Again, the phase might be wrong. So what we want to do is we want to do something that will change those phases to make them the right phases. And conjugating by a Pauli will do exactly that if we pick the right Pauli. Right? If A is 0, then we want something that commutes with X. If A is 1, we want something that anti-commutes with X. If B is 0, we want something that commutes with Z. If B is 1, we want something that anti-commutes with Z. So for instance, if you have A and B both 0, then you want to do the identity. That commutes with both. If they're both 1, then you want to do with Y. That anti-commutes with both. OK? And so you have all 4 possibilities and 4 Pauli. And so that gives you the last step that gets rid of these things and gets back the original state. OK? Yeah.
Okay, real quick question. How did you get the -1 to the A? Was that
Here.
just from...
Right. So I'm measuring here in the X basis, and I'm getting the output A, the classical bit.
Yeah.
OK? So if the classical bit is 0, that means I had the +1 eigenstate of X. If the classical bit is 1, that means I measured the -1 eigenstate of X.
Okay.
OK? And therefore, that should be in the stabilizer. That's just what 0 and 1 mean, plus 1 and minus 1 eigenvalues. Any other questions? Okay, so so long as you have a circuit consisting just of Clifford group gates and Pauli measurements, this is great. That means that it's very easy to simulate. You can keep track of what's going on, and you don't really even need a quantum computer to do that. You can just do it classically. The downside of that is that, well, we want to do some interesting quantum computations. And what this tells you is that if your quantum computer is a circuit that's only consisting of Clifford group gates, it's not going to do anything that's exponentially more powerful than a classical computer. So for instance, you definitely cannot do factoring. Well, okay. Definitely it's too strong because it's possible there's a classical factoring algorithm. But most likely you cannot do factoring using just Clifford group gates. Okay. So we have to ask, if we do want to do some more interesting quantum computations, Clifford group gates are nice. Suppose we have a bunch of them, but what else do we need? And it turns out that really just anything else will suffice. So in particular, if you look at the group, so if you take any unitary on n qubits, then, and you look at the group generated by the Clifford group on n qubits and u. So this is saying you can do Clifford group gates and some particular additional gate. Then this is a group which is dense in the unitary group. And so what does dense mean? It means that for any arbitrary v in SU2 to the n, you can get some product of Clifford group gates and U gates that gets arbitrarily close to v. Okay, so this is what's known as approximate universality. You can't necessarily exactly get the gate that you want to get, the unitary that you want to get, but you can get arbitrarily close, which is good enough. The upshot is that suppose, as you'll see with fault tolerance, that you have the ability to do Clifford group gates and some very specific additional gates. In fact, this only has to be a finite set of gates, right? So for instance, you work with 2 qubits, you get the 2-qubit Clifford group plus 1 additional gate. And once you do that, you can get arbitrarily close to arbitrary unitary. So this is going to be important in fault tolerance because we're going to have constructions, some of which will be complicated, to get fault tolerant implementations of specific gates, specific Clifford group gates and a few specific non-Clifford group gates. And we need to know that that's enough to be able to do arbitrary quantum algorithms. And this tells you that it is in fact enough. Okay? I'm not going to prove this theorem. It's fairly complicated. Actually, I don't really understand the proof. It's not so hard for certain specific gates to prove this, but to prove the general case, that's more complicated. Yeah?
So this doesn't tell us that you can get as close as you want to any unitary with a polynomial.
Right. This does not tell you that. So there's a question of polynomial in what? So there's 2 parameters. So okay. So there's yeah. So the most common case is U is going to be like a 2 or 3 qubit gate, something like that. And so then trying to get close to SU4 or SU8, now there's no n anymore. So you don't have to worry about that. Now, of course, once you have 2 or 3 qubit gates, whether you have them approximately or exactly, trying to get, if you have them exactly, you can kind of get exact n qubit gates, but that, of course, is going to be exponential in n. That's just unavoidable. The other thing you might want to do is say how many gates you need as a function of the approximation. So you want to get epsilon close to some gate. And it turns out, although this doesn't follow immediately from this theorem, this is another theorem that's also an important thing, that if you have an approximately universal set of gates, you can get epsilon close using a polynomial in the log of 1 over epsilon. So actually, you can, there is kind of very good fast approximation. And in the past, I don't know, 5 years or something, people have come up with specifically actually very good algorithms for getting good approximations, at least for if you have the single qubit Clifford group and specific common gates outside, then you want to approximate from that. So this theorem, that the general case of approximation with polylog is called the Solovay-Kitaev theorem. And if you kind of work out the numbers from that, they're kind of, you can work with them, but they're still pretty big for kind of reasonable approximations you want to get. But you can see huge improvements by using algorithms that are tailored for the specific gate set. And I don't know if those may just be even like linear in the logarithm of 1 over epsilon.
And that's for a specific U.
Yeah, so specifically, kind of the most common one people look at is the single qubit Clifford plus the pi over 8 rotation. So this is the square root of the pi over 4 rotation, which was one of the Clifford group gates that we had. And the 4th root of Z. Okay. So this is kind of one of the most common things that people look at. And of course, when you go to the so this by itself can't be universal for n qubits because it only has 1 qubit gates. But if you look at the 2 qubit Clifford group plus r pi over 8, that is universal now, because you can arbitrarily close to 2 qubit gates now, which is enough to get everything. And so that's kind of frequently the gate set that people look at when they're thinking about fault tolerance. But it's not the only one, but it's one of the more common. Okay. Okay. So are there questions on this before I go into a new topic? Okay. So the Clifford group. So for here I said, sure, if you have the Clifford group plus say the pi over 8 gate, then you can get arbitrarily close to any unitary. But the Clifford group itself is just a finite number of gates. That's fine. But nevertheless, it's actually, if you count them, it's relatively large number. It grows exponentially, for instance, as a function of n, the total number of gates. But of course, you don't really need to have every individual gate in the Clifford group, right? You probably just need a few that you can use to generate all the others by product. Okay. So how do we do that? Well, what we want to figure out is what gates generate the Clifford group. So actually, the ones that I showed you last week are in fact the generators. So we're going to talk about the n-qubit Clifford group, and it can be generated by C0, by the Hadamard, and by the pi over 4 phase rotation, up to global phases. Not so important. So any n-qubit gate can be Clifford group gate can be generated by products of these things. So let's see. So the 1-qubit case, I can show you that pretty quickly, right? So for 1 qubit, H, remember, switches X and Z. And the pi over 4 phase rotation switches X and Y. Okay. And for one qubit Clifford group gate, all you can do, any Clifford group gate is going to permute x, y, and z, right? And any permutation is possible. And so all we need is to kind of multiply these two things together to get arbitrary permutation. And you can see how to do that, right? If you want to send, well, I mean, one thing you could write it down. So there's 3 transpositions of 2 things. So here we have 2 of them. The third one, y and z. Well, you could get that by doing h, r power 4, and then h again. Right? You switch y to x, and then it goes to z, and x will go to y, and then it'll stay y, and sorry, x goes to z, and then it stays. Anyway, it's actually the right answer, right? If you conjugate this by this, then you're kind of switching the role of x and z. So you're switching z and y. And then if you take just the product of these 2 things, you're going to get a 3-cycle. Okay, and then you can get the inverse 3-cycle the other way. Okay, so that's all the 6 things that you can get up to Pauli's, and then you do some Pauli's, so this is the square root of z. So if you do this squared, you'll get z, and then h, z, h will give you x, and of course you can take the product of them to get y. So you certainly have the Pauli's here as well. Okay, and that will let you adjust the signs however you like. Okay, so that's the 1-qubit case. These h and r power 4 generated. For the 2-qubit case, or for the n-qubit case, we need to bring in the C0, and it's a little more complicated. So I don't want to give you a full proof, but I'll kind of sketch it, and I think the details are in the book. So what we're going to do is we're going to take some arbitrary Clifford group element, and we can write it I'm going to write it as a matrix, but not as a 2 to the n by 2 to the n matrix. I'm going to write it as a 2n by 2n matrix. So I'm going to go into the symplectic representation. And so the Clifford group acts on Pauli's, right, which in symplectic representation are 2n-bit binary vectors. So this is going to be a 2n by 2n matrix. We multiply it by a vector, which represents a Pauli, and we get another vector, which represents a new Pauli. And that matrix multiplication is going to give us the conjugation action of the Clifford group element. Okay? And the reason that works is because the conjugation action is a group homomorphism, so it respects group multiplication in the Pauli group, which corresponds to addition in the symplectic representation. So therefore, it's a linear algebra sort of thing where we multiply by a matrix. Okay, so anyway, so we're given this arbitrary element of the Clifford group in terms of its conjugation action on the Pauli's. And we want to know how to write that as a product of these generators. So what we're going to do is we're going to take that conjugation action and convert it into a matrix of this form. So it's a 2n by 2n matrix, A, B, C, D. And what I want to do is find some other matrices, Vi and Wj, a sequence of these things, where these are matrices built out of these things, or maybe even just individual ones of these, such that the product of Vi times U times the product of Wj is equal to the identity matrix. Okay? And then once I've done that, I can see that U is going to be a product, the inverse product of VI's times the inverse product of the WJ's. Okay? And so these things are going to be my decomposition, basically the circuit that implements U in terms of these generators. Okay? And so the way I'm going to do this is I'm going to say, well, each of these gates corresponds to some row or column operation on this matrix, okay, multiplying on the left or the right. And then by doing the appropriate set of row and column operations, I can reduce this into this form. Okay, so it's kind of a generalized form of Gaussian reduction. So let's write down what those things are. Okay, so for instance, if we have the Hadamard on the ith qubit, so what does that do? Well, you can work out that it switches the ith rows of AB and CD. Okay? And if you do it with right multiplication, then it switches the ith columns of A and C with ith columns of B and D. Okay? Again, I'm just asserting this, but hopefully you can believe it. So why should you believe this? Well, the kind of this is broken down into these lines represent X parts and Z parts, right? And so this is kind of the X input, X output part. And this is maybe the Z input, X output part, and the X input, Z output part, and Z input, Z output part. Okay? And so when I say I'm doing H on the ith qubit, well, I'm switching X and Z, but I'm only doing it on one side. So either I'm switching X and Z for the input or X and Z for the output. And so that corresponds to switching rows or columns. And AB, you see, is the top half, the X part, and CD is the bottom half, for instance. Or here, it's the left part and the right part. Okay. And so this adds the ith row of AB to the ith row of CD. And this is something similar for columns. So C naught is a little more complicated, so it adds the ith row of AB to the jth row of AB, and adds the jth row CD to the ith row. CD. Okay, so what's going on here? So again, R will map X to Y, which is X times Z. So you're adding an X part to a Z part, right? Adding ith row here to the ith row at the bottom. Whereas C naught, it takes Xi to XX. So you're adding one row up here to a different row up here. And IZ goes to ZZ. So you're adding one row down here to a different row down here, but in the opposite order, right? I to J, and here J to I. Okay? And so the basic strategy is, so using stuff like this, you can convert A into the identity matrix. Okay, you do some row additions. And you need these as well because A by itself might not have maximum rank, but together they kind of have to have rank n because everything is going to be independent. And so by swapping some rows forward with H or adding things appropriately, you can make that work. And then, for instance, you can use controlled Z, which you can get by Hadamard's and controlled not, which is going to row of so this is adding something from AB to CD. And so using then controlled Z's, you can kind of clear out C so that it's all zeros. Right. And then you have to maintain commutation relations. So kind of this is almost determined then. And then we have to just do some more stuff to get it exactly in this form. Basically, once you have this and this, in order to get the commutation right, this has to be I. This could still be something else, but then you can get rid of it using column operations or maybe more row operations. Column operations is probably better. Okay? That's just a sketch, obviously. Now, how many gates does this circuit end up being? Basically, we're doing a bunch of kind of Gaussian reduction type steps, each of which, potentially involves order n squared things because we have to add something maybe to every entry of the matrix in order to get it to work out. And so there's some constant times O of n squared. So it's O of n squared altogether. Now, it turns out you can get slightly better. You can actually do it with O of n squared over log n. That's a bit more complicated though. But anyway, the main thing to observe is that this decomposition in terms of generators is efficient, right? So you're not by switching. I mean, if somebody gives you this thing, it's a 2n by 2n matrix, so it's efficient to describe it, and you're not giving up that efficiency by saying I want to go to a representation as a product of generators, right? It's still going to be about the same size. Okay. So one more observation about this. So I said a couple of times that Clifford group could be used to make encoding circuits for stabilizer codes. And so this type of procedure is one way to do that, right? You say, okay, I have a stabilizer code. So that kind of partially specifies this unitary because I want to take the encoding circuit should take Z. So we start out with some qubits unspecified, and so those will have logical, xi and zi, and those qubits have to go to logical xi bar and zi bar stabilizer code. And then we have some extra qubits that start out as ancillas. We can start them as zeros. So there'll be eigenstates of z. And those should get mapped to the stabilizer generators. And so that specifies more of this matrix. And then there's a little bit more that kind of doesn't matter. You just have to pick anything that gets the commutation relations right. And then you have some u in this form. And then you can build the encoding circuit using a procedure like this. Okay? So this tells you, for instance, that stabilizer code can be encoded using an encoding circuit of size O of n squared over log n. Okay? Are there questions on this? Okay, so the next thing I want to say about the Clifford group is actually following up a question I was asked last week, which was about the Clifford group for Q-dits. So let me kind of repeat what I said, but write everything down and be a little more precise so you can actually see what it looks like. So again, I'm going to specialize to Q-dit with prime dimension. And it's going to be an odd prime. Okay, so so the first thing is basically what we can do is we can look at these generators and then try to get Q-dit analogs of them. So Hadamard switches X and Z. So we want something that does that for Q-dits. And that's the Fourier transform. And so the Fourier transform in the standard basis takes the basis state A and takes it to, this is a discrete Fourier transform. And here omega is the pth root of unity. Okay, so what does this do to Pauli's? Well, it takes X, you can work out to Z. This is the Q-dit X and Q-dit Z, remember? And it takes Z to X inverse. So this is where you see a difference from the Hadamard, right, which just took X to Z and Z to X. But of course, X inverse, the -1 for qubits, mod 2 is just 1. So it specializes to the qubit case. And you really needed that -1 here. Why? Because remember, the commutation relations are supposed to be preserved. And so X and Z will give you a factor of omega when you commute them past. But this is now in the opposite order. So you would get omega inverse if you just had Z and X. But when you have X to the -1, then you have omega inverse inverse. Okay? So it stays the same. And so the other one that has the obvious analog is the C0, and that has the analog of a sum gate, which is a 2-qubit gate that takes AB to A plus B mod P. Yeah?
Should that be omega to the AB or just omega to the A?
That should be omega to the AB. Thanks. Right, okay, so, and this is a sum gate, right? So this is the obvious analog, again, of C0. And what does it do? Well, it takes xi to xx, and ix goes to ix, zi goes to zi. And again, we have one small difference. Iz goes to z inverse z. And again, you need that inverse to make the commutation work out right. Okay? So then the next generator is this R part of a 4 gate. And it turns out that there's no very close analog of that for Q-dits. But from the point of view of generators of the Clifford group, what is important about it is this. That is taking X and adding it to Z. So it's basically taking X. So Y is not distinguished element anymore, right? But it is interesting to have something that takes X to X times Z. Okay, so let's come up with a gate that does that. And I have a name for this on the problem set. Yeah, call it R. So let's call it R. So R is going to take A to omega to the A minus 1 over 2 times A. So it's a phase gate, it's diagonal, but this is different, definitely different from what the pi over 4 phase gate was doing, right? The pi over 4, R pi over 4, was taking it to not a pth root of unity, but a fourth root of unity. And then it was just to a linear power A. Okay. This formula here, you see, it's clear that it doesn't have a good analog for qubits. Right? First of all, this over 2 is kind of ugly if you're dealing with mod 2 arithmetic. It's not meaningful. But even worse than that, A times A minus 1 is always 0. Right? Because either A or A minus 1 is 0. Okay? So this is something that's not a generalization of the qubit case. It's just something different. But when you work out what it does to Pauli's, it takes x to xz and z to z. So in that sense, it is clearly an analog of the pi over 4 gate. Okay? So again, it turns out that these 3 gates can generate the Clifford group. But there's another class of gates that's kind of interesting, which you can get out of these things, but it's still frequently interesting to write it down separately. And this is the scalar multiplication gate. I guess I also mentioned this last time. So for some fixed C in Z mod P, you have a gate S sub C, which takes A to A times C. So for qubits, you could also write down this gate, but it would just be trivial again, right? Because if C is 0, then it's not unitary. So C has to be non-zero. But if the alternative for qubits would be C was equal to 1, in which case it's just the identity. But for Q crits, you can look at C equals 2. And now something interesting is going on. And again, I should say A times C, and this is mod P. And so what does this do to Pauli's? Well, it takes x to the power C. And then to preserve commutation, Z is going to go to Z to the C inverse. And this is the multiplicative inverse of C mod P. Okay. Okay, so are there any questions on the Clifford group? Yeah.
The relationship between the symplectic group and the Clifford group, does that hold here?
Yes, it does. For the qubit Clifford group, remember it was symplectic. If you mod out the Pauli's and the phases, you get symplectic, the Z2, SP2NZ2, and here you have the same thing. But it's SP Z mod P. Right. And yeah, so no, Z mod P. So this is the n qubit Clifford group for qubits of size P. So each individual qubit is size P. Now you can also deal with prime power qubit. And then you have to go to finite fields, GFP to some power. But it's usually helpful to separate the number of qubits and the dimension. But it gets much more complicated and subtle when you deal with composite powers, which is why I'm leaving that out. Yeah.
Do these operations work the same way with the Gaussian elimination? Like, would all of the...
Yeah, pretty much. I mean, so Gaussian elimination now, I mean, this is all binary arithmetic, so Gaussian elimination is just addition, but now you also have to include scalar multiplication. But Z mod P is a field, so you have inverses, and so you can always, if you have, A here and B here, there's always something, vector A here and vector B here. You want to eliminate this element. As long as this one's non-zero, you can always multiply by something to make that happen. And so you have to add, sum to some power, right? Because if you do sum twice, you'll get A plus 2B, or A plus 3B, A plus 4B, and then you can get any coefficient. Okay. Any other questions? Okay. So then let's take a 10-minute break, and we'll come back and start talking about fault tolerance. So first questions. Are there second, not last opportunity, but another opportunity for questions in the Clifford group? Yes.
A kind of small one. So these hold for P being prime, right?
Yes.
So when you stop having it be prime, like the inverse thing clearly breaks down, right?
Right. So let's see. So if P is not prime, all of these things are well defined, except SC has to be only for C that's invertible. The thing that breaks down potentially, and actually I don't know what the answer is that these might not be generators of the Clifford group anymore.
What would cause it to stop working?
Well, this whole Gaussian reduction thing depended on having inverses, so that you could, like I said, if you have some row here and some row here, you want to eliminate an entry here, you add some multiple of this row. That's only possible if this entry in this particular place is an invertible thing.
Okay.
And there's a lot of stuff like that where you want to eliminate. This whole argument is eliminating things like that. So it might break down.
Okay.
And even the single qubit case can break down. It's actually not trivial to show that F and R generate the single qubit Clifford group. It's a little complicated, in fact. But and I don't know if that's true or not for qubits. Sorry, for non-prime qubits. Okay, other questions? Okay, so now I want to talk about fault tolerance. And so I want to start by kind of defining the basic model of fault tolerance that we're going to be working with. So, a lot of this is kind of subsumed in talking about the circuit model, but when you think about fault tolerance, there's a certain amount of physics that has to underlie this as well. And the question is, how much of that physics do we want to bring in? And how much can we do just kind of sticking to the circuit model? And so I'm going to write down a bunch of assumptions about the way things work, which I like to call the basic model of fault tolerance. And this basic model is used in kind of the vast majority of the papers that you'll see on fault tolerance. But it's never called that. It's never called anything, in fact. It's just, in some cases, a lot of these assumptions are not explicitly spelled out. They're just kind of assumed. But I think it's helpful to have a name so that you can start to talk about cases where it's different or not. And in any case, for class, I definitely want to kind of lay out carefully exactly what assumptions people usually make. So So the main thing we need to do here is, I mean, before we were talking about error correction, and so we only cared about errors in transmission, right? So what we need to do in this case is add in the possibility of errors during gates. And so this basic model is going to just work in the circuit model. So we're not thinking about alternative models of implementing quantum computing. And so a circuit is then, normally you think of it as a bunch of gates, maybe a C0 gate and a Hadamard gate. And even try, okay. And some other kind of gate. And you add in some additional qubits, and you do some measurements, and maybe you do stuff conditioned on measurements, and so on. Okay. Now, for the purposes of fault tolerance, what I want to do is break this not into a set of gates, but into a set of locations. And so a location, well, there's lots of different kinds of locations. So what kinds of locations are there? Well, there's gate locations. And so a gate location could be a single qubit gate location or a 2-qubit gate location, or a 3-qubit for that matter. And so the thing is that a 1-qubit gate location just affects that is just that 1 qubit. So a location, I should say, is supposed to be, to specify a location, you want to give both a position, which qubits is talking about, and a time. Okay, so for instance, this is one single qubit gate location. And this here is a 2-qubit gate location. So the single qubit gate location is just 1 qubit and a time. The 2-qubit gate location is 2 qubits and a time. And it's just still one location, even though it's affecting 2 qubits. And that's going to be important because we're going to add in errors per location. So why is it that I want to talk about locations instead of gates? Well, we have other kinds of locations that are not gate locations. So in particular, we also have state preparation locations. So this is an example here. Okay. And we want to include that because, things like that, preparing a state, that might not be perfect, right? So it could have error in it as well. And we want to include measurement locations. So for instance, the measurement might not be perfect, so that's a measurement location. And finally, we even want to include weight locations or storage locations. And so this is a big departure from the circuit model because we're including things like this, a location where we don't do any gate. But in a real fault-tolerant system, if a qubit sits around for a long time, it will accumulate error, right? So we have to include some error associated, even with not doing a gate. Now, of course, in some implementations, doing no gate is a lot more work than doing a gate, like NMR. But even in situations where you just leave it and that's how you implement a weight location, there's still the possibility of error occurring in that time. So you have to keep track of that as a separate thing for your error budget for fault tolerance. Now, what's not included in here is a classical computation location. So, and the reason for that is generally in this basic model, we assume that classical computation is perfect. So this is an assumption that you can relax. You can write down things that have classical computation locations, classical gate locations, and they can have errors as well. But that's a complication that that mostly people don't try to handle. It's one of these cases where if you do want to do it, that's kind of going beyond this basic model and doing something a little more complicated. Now, it turns out this is not an essential thing. You can kind of get all the same basic results about fault tolerance without that assumption. But for that reason, it's actually interesting to not think about it, because it's a complication that doesn't really change the basic picture. And so that's what we're looking for in this basic model, is something that kind of captures all the important elements of fault tolerance without being too complicated. As you'll see, fault tolerance can still be pretty complicated, so we don't want to add any extra complications to start with. Okay, so that's one simplification we're making already. Another simplification is kind of implicit in what I said, which is the assumption that we usually make, which is that all locations take the same amount of time. Just one time step, whatever that may be. Okay, and this is, again, not very realistic. Some things, measurement frequently takes longer than other kinds of gates, for instance. 2-qubit gates might take longer than 1-qubit gates, things like that. So first of all, if you have a big quantum computer, you kind of want to keep stuff in sync. So frequently it's the case that even if some gates are faster, you might want to wait around for your time step anyway. And again, this is something that's not really essential, but if you don't make it, it complicates the theory of fault tolerance. And so we'll leave it out of the basic model. Yeah?
When you say complicates the theory of fault tolerance, does the results still hold?
Yeah, that's what I mean. So that if some gates take longer and some gates are shorter, the basic results still hold. Depending on the circumstance. I mean, so in the worst case, you can do everything by just waiting until whatever the longest time step is.
Yeah.
If you wait that long for every gate, then you can kind of restore this situation. But then, of course, you need lower error rates to achieve that. So the theory part normally ignores that possibility and just says, then start everything at the same time. Yeah.
If you have like a really long wait, then would you break into 2 one-time steps, or would you then expand everything to be as long as your longest wait?
Yeah. So the main issue is this business about keeping stuff synchronized. So there's a few papers, not too many, but a few, that deal with fault tolerance when the waiting time for measurement is much longer. What you do then is you say, well, it's going to take some number of time steps, and I'm going to keep on doing other stuff during that time because I don't want to have to wait that long. But then you have to be careful when you do something that is based on the outcome of the measurement, that you have all the information you really need at that time. And so what you would Yeah, I mean, so what you do then is you have to kind of generalize this model a little bit to allow locations that have differing lengths. This would be probably the best rigorous way of doing that, although I'm not sure anybody has spelled it out in that much detail. Okay? Other questions? Okay, so one upshot of this breakdown into locations is the number of locations does not necessarily match the number of gates in the circuit. Right? If you have a sequential circuit with T gates in it involving n qubits, well, there's n qubits, each of which has to wait around for every time step that it doesn't have a gate. So the actual total number, because there's T time steps here, you're going to have n times t locations. Maybe plus or minus a little bit for state preparation and measurement at the end. Okay. Now, what we do allow is things like this, where we create qubits later on in the computation. So it could be that you'll have only a few qubits at the beginning, and then you add some more later on. So even if you have n qubits altogether, it might be less than n times t locations. You have to look at the actual circuit and kind of count it out. But the point is, it's not going to be the same as the number of gates necessarily, unless you happen to have a very kind of uniform circuit where every, well, no, even then. Yeah, if you have a very uniform circuit where every qubit has a gate at every time step, then yes, the number of locations is equal to the number of gates, plus or minus state preparation and measurement. But that's very rarely the case, right? Normally there's qubits waiting around, there's qubits coming, there's measurements in the middle, and so you have more or less locations based on that. When I said, yeah, so, but also remember that 2-qubit gate, yeah, so when I said there's n qubits and t time steps, there's at most n times t locations. And there could be less because of qubits coming later, but there also could be less because the 2-qubit gate, remember, affects 2 qubits, but is only 1 location. So if you had a circuit that consisted of only 2-qubit gates, then it would be, well, right, if it was all 2-qubit gates, then it would be like nt over 2. But if you have some weight locations, then it's going to be more than that. Yeah?
Suppose that we have 2 1-qubit gates that acts at the same time. Can
Sure.
we consider it as a 2-qubit gate?
Right. So something like this. So you have 2 options. So one is you can treat these as separate locations. So they're 2 1-qubit locations. The other option is to say, okay, this is going to be a certain kind of 2-qubit location. I wouldn't really call it a 2-qubit gate location because they're not interacting, but it's kind of a new kind of gate location that involves 2 1-qubit gates. Usually, it's not worthwhile doing that. There's certain cases where you might want to take certain, recurring subcircuits, like Bell measurement. And you can break that down into individual gates, or you can consider that as one location by itself. And so it's kind of dependent on exactly what kind of analysis you want to do, which one is a better thing to do. At this level, I don't really care what the gates are, right? Just I have a bunch of locations. Different kinds of locations correspond to different kinds of gates, and I can set those gates to be anything I want. The problem of having a 2-qubit location here is that you're going to have more such locations, right? Because you have h times u, you have h times h, you have h u times h. Those are all different locations then, different kinds of locations. Okay, that's why it's normally best to kind of break them up into the smallest thing to minimize the number of different kinds of locations. Yeah.
Last condition on the classical, like logical.
Yeah.
Gates. So are we going to actually account for like number of classical gates and the time?
Right. So in the basic model of fault tolerance, no. So we assume not only the classical gates are perfect, but that they're fast. So fast that we can kind of neglect the amount of time it takes. Obviously, that has to be an approximation. Otherwise, you could kind of say, oh, well, let's do exponential amount of classical communication. That shouldn't be allowed. We do want our circuits to be efficient in all the normal senses. And when we're counting resources, that's a reasonable thing to count. But in terms of modeling fault tolerance and error correction, usually people leave out this part. Okay? Like I said, not always. Sometimes they'll consider that. But again, for kind of getting the basic ideas of how fault tolerance work and getting all the basic results, this is the model that people usually use.
Do you know how many works that does take care of that, or like?
Yeah. I mean, so I should say most of the time that people relax this assumption, they're also relaxing this assumption.
Assume that the gate time for both of them are the same, like the quantum gate and classical gate.
Yeah, and that's kind of motivated. In some systems, actually, you don't want to do measurement, or maybe even can't do measurement in the middle of the computation. So that could be because it's slow. That could be just because it's very hard. That could be you only have a way of measuring all the qubits at once. And in that case, you actually need to implement the classical computation as quantum gates. It's just quantum gates where you don't really care about the phase. Okay. But yeah, I mean, I guess it's also reasonable to look at the case where the classical gates are not that fast and that you have to account for that time. Usually in these fault-tolerant protocols, you don't have to do a ton of classical computation. That's not exactly true. So the main classical overhead comes from the decoding algorithms, is determining the error syndrome. Determining the error given the error syndrome. And so you want a error correcting code that's good at that. Okay. Other questions so far? Okay. So the next element. Okay. Maybe I should have started back on the other end. Okay. So the next element of the basic model has to be how we deal with errors. So this is something that does vary a lot between papers. People will talk about different kinds of error models. And they all pretty much work on the idea that so that the errors kind of work based on location. So you're going to have kind of one kind of error that affects storage locations, another kind of error that affects gate locations, and maybe even a different one for single qubit gates versus 2-qubit gates, measurement locations, storage. They could all in principle have different kinds of errors. And the most common thing you'll see is the assumption that you have an independent stochastic error model. So in the independent stochastic error model, so location L has probability P sub L of some error, which is some quantum channel. And then with probability 1 minus P sub L, it has no error, in which case the location behaves in exactly the way it's supposed to. So this is called a faulty location. And you say that there's a fault, that location is a fault. Yeah, so and in this basic model, usually this probability here only depends on the type of location, right? I mean, you could easily generalize it so that, gates at the beginning of the computation have a lower error rate than gates at the end of the computation, even for the same type of gate. But mostly people don't do that. Okay. Now, there is some flexibility here because this channel, depending on the work that you're talking about, it might be exactly specified, like this is a depolarizing channel. But it might not be specified at all. It could be just some arbitrary single qubit channel. Okay. Now the thing that makes this stochastic is this probability. And what makes it independent is two things. First of all, that this probability is uncorrelated from location to location, and that the channel is uncorrelated. So let me point out that this stochastic thing is already a pretty big assumption, right? Because even if you want to be independent, so you say what's happening on different locations is totally unrelated to what's happening on other locations. You could say, well, but you're going to have some quantum channel that's the actual location. This is stronger than that. This is saying that we have some definite probability that we're getting the right thing. Okay? And so, for instance, this doesn't include, or at least in a non-trivial way, I mean, it would have 100% probability of error, a channel where you do the gate U, but then there's some small additional rotation that happens every time. Even, or the case even where there's some small additional rotation, but the exact amount of the rotation is random. Okay? Those are perfectly reasonable error models, and they're not included in this, except in the extreme case of 100% error probability, which would then lead you to think that everything is bad. Okay. So again, this is an assumption that we're making, not because it necessarily represents the real world, but because it allows us to analyze these systems. It's a very useful simplification, and yet kind of basically the same results still hold when you relax that assumption. Yeah, and so I should say that this independent one is also something that you can relax. You can deal with cases where there's correlations, and even where there's some non-Markovian errors that are occurring, where there's some memory that interacts repeatedly with the system. Okay, so as I said, in the basic model, PL only depends on location type. And often, it doesn't even depend on that. So often, different location types will have be considered to have the same error rate. So, for instance, you might assume that the preparation error rate and the gate error rate and the measurement error rate are all the same. But maybe the storage error rate is less. Note that it doesn't make sense to have the storage error rate be higher than the gate error rate. I mean, you can imagine it, but storage error rate kind of represents the amount of error that happens in your system, even if you're not doing anything. And adding a gate on top of that should add extra errors, right? Because your gate might not be perfect. There might be specific systems, like I said, where you have to do some work to do nothing. But in most cases, you would think of the cases storage error rate being less. But sometimes people don't even want to assume that. For simplicity, you might even assume it's the same as these as well. Okay. Again, this is not something that's supposed to be realistic. This is just a simplification that makes it easier to work with. Okay? Yeah.
So I can imagine, for example, is there restrictions on the channels that you're applying? In general.
Not really. Okay. So within the basic model, no, there's no restrictions. people will usually, I mean, even this stochastic error model is kind of a little bit more specific than the general basic model because it's not totally uniform. People will say, oh, this is something that people do say frequently, that I'm dealing with this error model. This type of stuff is what they'll lay out. That stuff, they won't usually. That stuff is assumed. Okay? And usually, well, okay, so there's kind of, depends on what you're doing. So if you're doing a simulation, then usually they'll specify a very specific channel. Usually a depolarizing channel, but not always. Okay? And that's what happens when you get a fault. If you're doing a proof, you don't usually want to make an assumption like that. And then it can be any channel, including an unknown channel. You don't have to know what it is. But almost always one that takes, say, qubits to qubits. Okay? Sometimes people also think about erasure channels, which is kind of the general case, or one possible general case where you take qubit to some larger Hilbert space, or smaller for that matter, and then you have to replace the thing that gets thrown out.
So what I had in mind is, for example, you can change, or can you change the value of PL, for example, by kind of merging that into the channel?
Yes, you can. So normally what you want to do is you want to pick the smallest value of PL that's compatible with the errors that you're considering. Why is that? Because in my fault-tolerant analysis, I kind of ignoring the details of what this is. And what I'm going to do is I'm going to say, what's the probability that I have so many faulty locations? And can I recover from that? And so by making this as small as possible, then you're kind of getting the best understanding of how many faulty locations you really do have. Okay. Yeah.
So there's a 1 minus p and p in like depolarizing channel. Is this that p or
right? So when yeah. So if you are doing something like the depolarizing channel, then it's already of this form, and so yeah. So the 1 minus p, in order to make this as small as possible, you want it to be just the ones that have errors. So you have 1 minus p identity, and then p over 3x, p over 3y, p over 3z, and that's what's in here. So this thing is then not actually a depolarizing channel; it's an XYZ channel of some sort. Yeah, so that's actually an example of how you kind of can trade off these two things. Because you would also say, well, this one is now the totally depolarizing channel. But that makes this a little bit larger. Right now it's 4/3 of that p. Because a quarter of the time when you do polarizing channel, you totally depolarizing, you still get the identity.
So which one do people usually do? Like you run the thing through depolarizing every time?
Well then, I mean, they're doing a simulation, so it doesn't, this breakdown doesn't matter as much because they're tracking every error now, every Pauli error. But like I said, in keeping with this analysis, the best way to do this would be the kind of the px plus py plus pz part would be the fault.
And how do we simulate, like what is if we do the gate,
Yeah.
and on the, like if we have a 2-qubit gate, we run the depolarizing channel on the both outcomes?
Yeah, so people do different things, but usually what it means is that they pick some error probability, and they say with 1 minus that probability, the gate is perfect. And I think the most common thing is to say, if you do have an error, it could be any 2-qubit Pauli. Non-trivial, I assume. But I've never actually done this simulation, so I don't know. Yeah.
Sorry, I can see, but it says the channel is independent of the probability of fault and channel uncorrelated between locations?
Yeah.
So the channel uncorrelated between location.
Yeah. So so for instance, so let me give you examples where it's not true. Maybe that's the best thing. So one easy way to have correlations is to say, well, I have these two locations here. The probability of having an error on this location by itself is P1. The probability of this location by itself is P2. If they're uncorrelated, the probability of having errors on both is P1, P2. If they're correlated, it might be more than that, or less than that. Okay? but it's still the case, even if the probability of having faults on both of these locations is P1 times P2, that if you happen to have faults on both locations, that what happens to them, the actual channel, is a 2-qubit channel that connects the two of them. Okay? So that would be another example where it's not independent anymore, even though the probability of faults is independent. Okay?
Okay, so then you're saying a lot of papers would do the same assumption where they assume the channel is uncorrelated between locations?
Yes.
But doesn't that seem a little bit unreasonable in the sense that, well, not super realistic?
No. Okay. So what does it mean for the channel to be uncorrelated? I mean that the channel that occurs on these two faulty locations, let's assume they're at the same time, would be C1 tensor C2. Okay, but each of C1 and C2 includes some randomness and it includes some error modeling. So it could be, for instance, that every Hadamard gate has the same kind of channel occurring, which might be over rotation by some theta, over rotation by some theta, which is drawn from some distribution. And it's the same distribution every time, but that's still a tensor product channel. Okay.
Yeah.
Now, if theta is drawn from some distribution, but then it's always the same theta, then it's not independent anymore. Okay.
But
or you can still think of it as independent. It's just it happens to be rotation by this fixed amount, which is picked some externally to your protocol. So let's and then it's just we don't happen to know what it is. Okay. So maybe a better example where it really is correlated is you say at time 1, every Hadamard gate experiences over-rotation by angle theta. At time 2, it's by theta 2, or theta prime, which is different, but it's still the same for every gate at that time. No, even that you can write this way, because you have to go beyond the basic model and have the channels depend on the time as well as the type of location. But anyway, you get the idea that there's randomness involved in the channel, and as long as the randomness in the channel is kind of independent from time to time, then that's still independent. And it's only if the randomness becomes correlated that you get something that's not independent.
So there are a lot of papers on that area where the channels are correlated?
Well,
aren't
sort of. In the sense that when you're doing proofs, usually what you care about is whether there's a fault or not, and then you don't want to make too many assumptions about the channel itself, and therefore it doesn't actually matter whether the channel is correlated between different faulty locations or not. Okay, so it does include cases where they're not independent.
So like this assumption wouldn't change the main results too much.
That's right. And in fact, the threshold theorem, which you'll hear about from Benny in a few weeks, is it actually kind of needs to go beyond this model to have correlated channels here. And the reason for that is that the logical channels that you get become correlated in the channel sense, whether or not the physical error model is that way. Okay. So there are other questions. Okay, so right. So this is kind of the basic model of locations, the basic model of errors that people talk about. Now, what I haven't said is anything about what a fault-tolerant circuit is. And so this is not really assumptions anymore so much as the structure of the protocols that people usually think about. So fault-tolerant protocol is a circuit encoding. So what it is a map from unencoded circuits. So this is the ideal circuit that you want to implement to encoded circuits. And it should have the property that at the end of the encoded circuit, you make some measurements. At the end of the ideal circuit, you're making some measurements to get some classical output. And then there'll be some classical decoding procedure that gives you the, in the absence of errors, if there are no errors, this should be the same as the output of the ideal protocol, the ideal circuit. Okay? So that's the sense in which this encoded circuit represents this unencoded circuit. So if this circuit is C, I might represent this encoded one as ft of C. Yeah?
Is this for like a one-shot measurement, or can this be the classical decoding for like an accumulation of a measurement?
Yeah, so normally, so again, this is in the absence of errors. Normally, the circuit encodings that people talk about will have the same distribution of outputs once you do this decoding. And so that's true for one shot as well as for, of course, accumulated. Yeah, I mean, sure, you could expand definition to allow other possibilities. Yeah, I can't think of a case where you actually do that. Yeah, but I don't see any kind of fundamental reason why you wouldn't want to do that.
Okay.
Yeah, I mean the main thing you want to bear in mind is that this is supposed to be a map that works for a very big class of circuits, ideally arbitrary circuits or a universal set of circuits. And so it's probably hard to come up with something that has the right expectation values over many things, but the individual distribution is not right. And in fact, I mean, even this general circuit encoding that I've written is not used in real protocols. Usually it's something very specific, which is you take ideal locations. Well, okay, so first of all, we're using quantum error correcting codes. So we're going to have qubits, and we're going to encode them in quantum error correcting code. So there'd be the logical qubits. Then each location in this ideal circuit will get mapped to something called a gadget. Okay, which represents this location, which is supposed to do this location effectively on the encoded state. And so these are more often called, I guess, logical locations. And so the gadget itself, of course, is made up a bunch of, you also have some circuit representation of that. So it's composed of physical location. In just the same way that the logical qubits of the quantum error correcting code are encoded in a code that is made up of physical qubits. More physical qubits. Okay, and most often, so usually what you'll do is you'll take some circuit, and you'll take each location here, and you'll convert it into the corresponding gadget type. Okay, and then between these gadgets, you'll insert error correction steps. So for instance, if we had a circuit, a simple circuit like this, and we might convert it to, some C0 gadget.
Okay, let's go down.
And then error correction on both qubits. And then here we have a Hadamard gadget and a wait gadget, which is probably just waiting. And then you do error correction again, and so on. Okay? And this is not essential, but in some cases it might be better to wait and not do error correction immediately. But certainly in terms of analysis, this is much easier to break it down into kind of small components. Okay? Yeah, so I guess one other thing I wanted to point out is that, the quantum error correcting codes we'll be dealing with. So in the previous part of the course, we were saying, okay, quantum error correcting code corrects T errors, and we'll assume that there's at most T errors, because the probability of getting more than T errors is very small. The problem is that now in fault tolerance, we tend to talk about very big circuits with many, many locations, possibly many, many qubits. And it's no longer safe to assume, if you look at some small area, some small number of locations, sure, the number of errors or faults is going to be, with high probability, it's going to be very small when P is small. But if you look at the whole thing, there will be many, many faults altogether, okay, because it is a big circuit. And so usually we're kind of shifting to a different model where we're not trying to correct all sets of faults of up to size T. Instead, we might want to correct typical fault arrangements with a probability of P of fault per location. And what that boils down to is that if we look at a small region of the circuit, we might well make this assumption no more than T faults in it. But in the circuit as a whole, we're allowing many more faults. It's because we don't want them to be too concentrated, okay? Because that doesn't happen too much in the typical case. Okay? So exactly dealing with this kind of trade-off is something that will come in later when we talk about the threshold. But I just wanted to kind of prepare you for that. Okay? So anything else about these modeling and kind of what a fault-tolerant protocol is? Yeah?
So assuming that the classical gates are perfect, then what if we are doing less number of EC blocks, right?
Sorry, doing what?
Less number of error correction. Might as well do it every time. And especially if
it doesn't, it might play into your trade-off, but it's kind of not really the same issue.
So we didn't model, like, if the gates are not fast, for example, there should be memory error there, but But if we don't have that, then we might want to just do it every time after a gate.
No, well, oh yeah, so okay, so if we don't have any storage errors, if you model storage is perfect, then certainly it doesn't make sense to do error correction after just a wait step. But if you're doing other gates, quantum gates, then even in that circumstance, it might make sense to do error correction every time. So the real trade-off that you're playing with is that these error correction steps have to be fault tolerant themselves in ways that I'll talk about in a little bit. And that makes them pretty complicated. Okay? And so you have to trade off. Well, so first of all, that means it takes more time. But more importantly, in the context of fault tolerance, all the gates that you're putting into these error correction gadgets can themselves have errors. And so you're introducing more errors while you're doing the error correction. And you have to trade that off against the fact that you're correcting errors too. So if you kind of wait the right amount of time, then, which could be very short, then you're correcting more errors than you're introducing. Well, okay, if you're not correcting more errors than you're introducing, then it's not going to work at all. But the question is kind of how much of an advantage you're getting. And maybe, waiting for a few gates, you get more advantage or less advantage. And there's only been really a couple of papers kind of looking at this trade-off. I don't think there's a clear-cut answer. But usually people just assume you kind of do it almost as often as you can because because that prevents the errors from building up. And if they build up too much, then that's when you know it's going to be a problem. If you wait too long, that's definitely bad. Too short might be better or worse than a little bit longer, but it's definitely not going to kill you, whereas waiting too long will kill you. Okay. Okay. So what kinds of issues are we going to have to deal with in these gadgets to make fault-tolerant gadgets? So the first one is, well, we have the qubits now encoded as logical qubits of a quantum error-correcting code, which means that if we want to do a gate, it's not nearly as simple as just taking one qubit and doing something to it, because a single qubit is not going to change the gate, right? If you take a quantum error-correcting code and you change one qubit, that's also known as an error. So you have to do something on a bunch of qubits at once, and you have to do it in such a way that you never lose the protection of the quantum error-correcting code. Right? One way to do gates would be to say, oh, I'm going to decode it, and then I'm going to do the gate, and then I'm going to re-encode it. But obviously, that's not going to work, right? Because if you have a fault during the decoding or encoding procedure, or while you're done, or while you're decoded and doing the gate, then that would kill you, right? That would be a logical error. So we need some way without ever leaving the code space, or at least leaving some space that has the same error correction properties as the code space. So that's one issue we're going to have to deal with. But the other one is we have to really be careful about how we do these things. So what we have to worry about really is error propagation. So to illustrate this, so error propagation shows up when we have a 2-qubit gate. So let's think about the C0 gate, and let's look at a very simple case where we have just 2 qubits here. And the input state is supposed to be 0, 0. Okay? When we do the C0, the output state could also be 0, 0. Right. But what happens if there's an error? So in this case, the C0 gate is not going to be faulty. The C0 gate is going to do what it's supposed to do. So the error is a pre-existing error. And suppose this input state is 1 instead of 0. Well, then what's the output state? Well, now it's 1, 1, right? So the fault, well, there's no fault. The error has spread the second qubit. Okay, this control not propagated it. So of course, this kind of thing also occurs in classical systems if you have errors. But in quantum systems, it's actually even worse than that. So let's consider again this same C0 gate. But now we're going to do it on the input state ++. Okay? Well, the target here will flip the second qubit if the first qubit, sorry, this target qubit will get flipped if the first qubit is 1. But the target qubit is in 0 + 1. So flipping it doesn't do anything. Okay? So the output should be ++. Okay? Now let's assume that this is a minus instead of a plus. Okay? Again, there's an error in the input. Well, when the control is a 0, it's going to stay a minus. When the control qubit is 1, this will get flipped. 0 minus 1 becomes 1 minus 0. So it's minus, minus. Okay? So either way, we get minus down here. But if we have 0 up here, we just get minus. If we have 1, we get an extra phase. So we started with 0 + 1 up here, and now we have 0 minus 1. And so the top part is also minus. Okay? So the C0 has propagated the phase error from the target qubit to the control qubit. And that's not something that happens classically. Classically, this control qubit just stays the same. And it's only the target that can change. Okay? So this is something extra that we have to deal with in quantum computing, that errors will propagate both ways along these gates. So this particular example, you can also understand C0, of course, is a Clifford group gate. And what is this? This is a bit flip error. It's an X. And so it's propagated to XX, right? XI propagates to XX, as we saw. And here, this is IZ propagates to ZZ. So this business about errors propagating forward and backwards was already implicit in the conjugation rules for C0 acting on polys. Okay? So, so how can we avoid error propagation? Well, one easy way to do it would be to only do single qubit gates. Right? If we do a single qubit gate, we can't propagate errors. That means that an error that we have that's pre-existing, well, it can still affect that same qubit, but it won't affect more qubits. Oh, I could say why, but of course we don't want to just stick to single qubit errors. We're going to single qubit gates. We're going to have to do some 2-qubit gates somewhere. So let's think a little bit more about why error propagation is a problem exactly. So suppose you're using, say, the 7-qubit code. Okay? And you're going along, one error happens, and then you do a C0 gate between 2 qubits in the code. So now this one error could propagate to a second qubit. 7-qubit code can correct one error. It can't correct 2 errors. At least not 2 errors of the same type, like this. Okay? So before you had an uncorrectable error. Now, even though you have had no new fault, the C0 was acting correctly, you started with a correctable error, now you have an uncorrectable error. Okay, that's bad. That's what we want to avoid. But look what happens if instead of doing a C0, suppose we have 2, I'm only going to draw 3 lines, but pretend it's a 7-qubit code. Suppose we do a C0 from here to here. Okay, these are 2 separate blocks of the 7-qubit code. Well, if we started with an error up here, that was correctable in this block. And now we have 1 error up here and 1 error down here. That's correctable as well, right? Because this block can correct 1 error, this block can correct 1 error. So that's okay. Okay? And in fact, what we can do is, if we want, we can do C0s like this. Always from one block to another block. And if there's just 1 error up here, then it will end up with at most one error up here and one error down here. And that's acceptable. So this is called a transversal gate. And so specifically, a transversal gate is one that interacts the ith qubit of one block only with the ith qubits of other blocks. Okay, so by this definition, so this thing that I've drawn here is transversal because the first qubit interacts with the first qubit, the second qubit interacts with the second qubit, the third qubit with the third qubit. If I did something like this, that would not be considered transversal. Okay? Because here the second qubit is interacting with the first qubit of this block. Now, why is this okay and this bad? I mean, this still so this thing still has only gates interacting the first block with the second block, right? But let's look what possibilities we have. So certainly if we have an error up here, it'll propagate down here, like an x error up here will propagate down here. We'll have one x and one x. That's okay. But suppose we had a z error down here. Well, there's still only one z error down here, but now there's two z errors up here. Okay, so that's bad. So, I mean, you can sometimes get away with non-transversal gates, but you have to be very careful about how you do it. Okay, and you know, there's other, depending on what the gates are, you have to worry about possibilities like this, where something propagates to two different locations up here. You have to worry about cases where something starts up here and then propagates down here and then propagates back to a different qubit. If it propagates back to the same qubit, that's okay. But if it propagates back to a different qubit, then that would be a problem. Okay, and so these are the sorts of things that can arise with non-transversal gates. And so that's why we like to stick to these transversal gates. But if we have the transversal gate, then error propagation is under control. Okay? It still happens with two-qubit gate, but only happens between blocks, and the weight of the resulting error on per block will not increase. Okay. So does everyone understand what a transversal gate is? Okay, so let's see some examples. Okay, so for any stabilizer code, so one easy way of getting transversal gates is to do single qubit gates, right? Single qubit gates are automatically transversal, right? Because they're interacting the ith qubit only with itself of the block. But we still, to get something fault tolerant, we still have to do this other problem of staying inside the code space, right? We want to map code words to code words. And for stabilizer code, the logical polys can at least be implemented this way. Why? Well, we know, remember, that n of s mod s is isomorphic to the logical polygroup. Okay? And so what we can do is we can take any such coset representative, and it's a tensor product of polys. Okay? So it's a single qubit tensor product, single qubit gate, so it's transversal. And these are things that map code words to different code words. So before I was calling that an undetectable error. Now I call it a fault-tolerant gate, right? And the difference, of course, is whether it happens accidentally or deliberately. Okay, so that's easy. But that just gives us logical polys. We'd like to do more than that. So it turns out the 7-qubit code is particularly good for transversal gate, and transversal Clifford group gates in particular. So let me write down the stabilizer again. And then the logical x is, for instance, all x's. And the logical z is all z's. Okay, so now I want to figure out transversal implementations of logical Clifford group gates. And I'm going to do them via some physical Clifford group gates. So what happens to a stabilizer code if I do a Clifford group gate? So if we have some m in the stabilizer, the Clifford group operation u will map it to u dagger. Okay? And so for you to preserve the code space, we want u dagger to be in the stabilizer, the original stabilizer, right? So u dagger is in the new stabilizer, which we want to be the same as the old stabilizer. So and this needs to be true for every m in the stabilizer. Okay? So let's think about that in the context of the 7-qubit code. Okay, so what can we do that involves Cliffords that will map these stabilizer elements to potentially different stabilizer elements? But they all have to stay in the stabilizer. Well, one example so one easy example is the transversal Hadamard gate. So if you do 7 Hadamards, one on each qubit, what happens? Well, this ZZZZ becomes XXXX. And this becomes this becomes this, and vice versa. Okay? So you can immediately see that this implements some sort of logical operation. Is transforming the 7-qubit code to itself. So what logical operation does it do? Well, we can figure that out by tracking what happens to the logical x and z. So what does it do? It takes the logical x is 7 x's to 7 z's, which is the logical z. And the logical z goes to the logical x. Okay. So what we have some logical gate that switches the logical x and the logical z. Well, we know what that is. That's the logical Hadamard transform. Okay? And so again, I'm putting this bar over the H to indicate that it's the logical version of it. Okay? So, so what else can we do? So I claim that if we do the tensor product of R, 7 copies of R pi over 4, we'll also get a logical gate. How can you see that? Well, what does R pi over 4 do? It takes Z to Z, so these 3 generators stay the same. And it takes X to Y, which is I X times Y. Sorry, X times Z. Okay? So it takes like X, 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 X to Y, 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 which is the product of X's and Z's. So it takes this thing to the product of this and this, which is in the stabilizer, right? So it's not necessary that we take the generators to generators of the stabilizer. We just have to go to elements of the stabilizer, okay? Which will be generators, a different set of generators that you could have chosen, of course. So this is also a logical operation. And what does it do? Well, it takes Z bar to Z bar, of course, and it takes X bar. So this is a little more tricky. It takes X bar to 7 Ys. Okay, so if we take the product of X bar and Z bar, what do we get? Well, we get 7 Ys, but each time we do it, we get a factor of I. Well, minus I. Okay, and we take minus, so in this case, we're multiplying 4 x's and 4 z's. And so minus I to the 4th is just 1. So that didn't matter. But minus I to the 7th is not 1. And so if you work it out, what you actually get is this is going to minus I x bar z bar, which is not y, but it's minus y. And so what that's saying is that the transversal pi over 4 gate is actually the minus pi over 4 logical gate. Okay? This is an example of why you have to be a little careful sometimes about these signs. You get everything to work out right. Okay? So what else do we have? So this is remember, generators of the single qubit Clifford group gate. So what about C naught? Well, suppose we do the transversal C naught. So this is the 7 qubit version of that. Well, what does that do to the stabilizer? Okay, now we have to think about 2 copies of the stabilizer. Right? There's this, and there's another copy of it down here over here on 7 additional qubits. And you can think of that as a big stabilizer with twice as many generators. Some of the generators of this thing tensor all i's, and some of them are all i's tensor copies of this. Okay? And so what happens when we apply this transversal C naught? Well, z, all i's, is just going to go to itself. Right? Because z tensor I goes to itself 7 times. Well, 4 times anyway. And similarly for these. On the other hand, x tensor all i's, that's going to go to xxxx tensor xxxx I. And again, that's a product of this generator with the corresponding generator on the second block. And similarly for this and this generator. Now we also have to look at generators on the second block. So we have IX generators. Those go to themselves. And IZ generators. So I, and then ZZZZ, for instance. And that will go to ZZZZ on the first block, tensor ZZZZ on the second block. Okay? So it's, again, a product of this generator with the corresponding one on the second block. That's OK, too. Okay? And if you think about it, actually, this wasn't specific to the 7-qubit code. It works for any CSS code. So any CSS code is constructed by having some generators here that are all z's and some that are all x's. And that was really the only property that I needed. The all x's ones get just copied over from the first to the second, and the all z ones get copied over from the second to the first. Okay? So then let's work out what logical gate it does. Well, it's kind of the same thing, right? The logical x is a tensor product of x's. So x bar tensor I goes to x bar tensor x bar, etc. And so again, you're doing the logical C naught. Okay? And so what this tells you is that we can implement all the generators of the logical Clifford group using transversal gates for the 7-qubit code. And this is one reason why the 7-qubit code is very attractive for fault tolerance, because you have a whole bunch of gates, you have the whole Clifford group can be implemented transversally. Yeah?
Oh, so are you implying, like, for the 5-qubit code that the C naught is not transversal?
That's correct. Yeah, maybe I'll quickly do that. So let's work it out. Okay, so what happens when we do the C naught tensor 5? Well, it'll map x, z, z, x, I on the first block. So then tensor I will get mapped to x, z, z, x, I, tensor x, I, x, I. Now, this part is in the original stabilizer. So we could multiply by it. And then we're left with xii, xi. So if this whole thing is in the original stabilizer, then this part, xii, xi, would have to be. But it's not. You can just see that. And therefore, no, this C naught tensor 5 does not preserve the code space. Okay? In fact, it's the case, I mean, I didn't say this, but to be more explicit, the transversal C naught is a valid logical operation for any CSS code. And those are the only codes for which is a valid transversal operation. Yeah?
Here we kind of took advantage of the fact that the logical X and Z have like transversal representatives, if that's a thing.
Well, right. So but that's true, of course, of any stabilizer code. Right? Because any stabilizer code, the logical polys can be represented as a tensor product. They'll be represented by some n-qubit physical poly. I mean, in this case, we're taking advantage of the fact that the x is a tensor product of x's and z is a tensor product of z's. But we didn't need that to do this analysis. It was useful for the actual results that we had. And that's not, of course, true in general. But. Okay? So anyway, so for 7-qubit code, we have all the Clifford group. So that's really nice. Unfortunately, as we just saw, the Clifford group is not universal. You're going to need something else outside. And unfortunately, this is the end of the transversal gates for the 7-qubit code. So if you want to do fault tolerance for 7-qubit code, you have to do something else, which we probably won't get to next week, maybe the week after. Nevertheless, at least it gives you a good starting point of a bunch of things. OK, so that's it for today. Are there any more questions on transversal gates? OK, so then problem sets. Turn in your problem set. If you didn't get a new one, here's new ones. I think we have the graded ones. So let's see. I also have a couple of graded ones from the first problem set. John, you have the, yeah.